Hi there, this is Waves, Lesson 6, Standing Waves, Part 4, and we're going to do 3 exam-style questions. So first of all, a bit of a recap. Explain how a stationary wave is produced when a stretched string is plucked. So off you go, pause the video, write down an explanation. Right, I'll take you through the answer. So waves would travel to the boundary and are reflected. The two waves travelling in opposite directions would undergo superposition, or you could say interfere or superpose. In some positions, the waves always cancel or interfere destructively to give zero amplitude, which we call nodes, or they interfere constructively to produce positions of maximum amplitude or maximum vibration, and we call these antinodes. So, quick reminder. Let's draw the second overtone. These positions are where we get interfering destructively to give zero amplitude, and we call these nodes. So each of these circles that I've drawn is a node, and then we also get positions of maximum amplitude or maximum vibration, the antinodes. So that's this region of space. So hopefully that's okay now. We've done that a few times. Let's move on. So next I want you to pause the video and have a go at this, and then I'll take you through the answer. The vibrating length of one of the strings of a violin is 0.33 meters. When the tension in the string is 25 newtons, the string vibrates with a first harmonic frequency of 370 Hertz. Part 1. Calculate the mass per 1 meter length of the string. So we've got the first harmonic frequency, 370 Hertz. We've got the length, L, 0.33 meters. And we've also got the tension in the string, 25 newtons. So this should be pretty straightforward. So frequency is equal to 1 over 2L, square root tension divided by mu, the mass per unit length. So let's square this and rearrange to find mu. So F squared is equal to, so that would be 1 over 4L squared, but then the root's removed from the T, so we can just write T at the top, divided by 4L squared times mu. And then rearrange to get the mass per unit length. So mass per unit length is equal to tension divided by 4L squared F squared. Then we just simply need to put our numbers in. So the mass per unit length is equal to 25 divided by 4 times L squared, so times 0.33 squared, times the frequency squared, 370 squared, the fundamental frequency. Put that in our calculators, and we get mu, the mass per unit length, to be 4.2 times 10 to the minus 4 kilograms per meter. Hopefully that's okay. So I'm just going to remove this and then do the next part, part 2. The first harmonic vibrates at a frequency of 370 Hertz. Calculate the speed of the wave. So wave speed, V equals F lambda. So we've got the frequency, the 370, multiplied by the wavelength. So we have to be careful with this because what we've got is the first harmonic at 0.33 meters. And you can see from the diagram that that's half a wavelength. So the full wavelength would be 0.33 times 2, which is of course 0.66 meters. So we can finish this at the top, 370 Hertz multiplied by a wavelength of 0.66 meters, which gives us a wave speed of 244 meters per second. Hopefully that went okay. Let's try one more. So we've got an experiment here that a student might set up, and it says, well, first of all, you should pause and have a go, and then I'll take you through it. But it says, the nylon string using the above experiment, or the side experiment, by a student has a density of 1,150 kilograms per cubic meter, and a uniform diameter of 5 times 10 to the minus 4 meters. Determine the length L of the string used if a mass of 0.5 kilograms produces a first overtone of 220 Hertz. So there's a lot of information there, and we actually have a lot of things to do as well. So the first thing we should do is find the mass per unit length. So let's have a look at this. So mass per unit length would be mass over length. But we don't have mass, we have density. And mass is density times volume. So we've got density times volume divided by length. And volume divided by length would be density times cross-sectional area. So we can do that. So we've got the density and the diameter. So let's look at that. So density times area. So 1,150 kilograms per cubic meter multiplied by the area. So the area would be pi r squared. So we multiply by pi times, the radius is half the diameter, so it's 2.5 times 10 to the minus 4 squared. So that would give a mass per unit length of 2.258 times 10 to the minus 4 kilograms per meter. So that's the first part done. So if you've not got this, get it written down. Move on to the next bit. We also need the tension. We've got the mass, so we can find the tension. So mass of 0.5, so tension is mg. So 0.5 times 9.81, which gives a tension of 4.905 newtons. The next thing we need to think about is the first overtone of 220 Hertz. Now the equation, the frequency is 1 over 2L square root T over mu, is for the fundamental frequency. So if I sketch this diagram, for whatever length this is, the first overtone is the second harmonic, which looks like this. So if the frequency is 220, if we were to actually find the first overtone for the same distance L, the first overtone would look like this. So if the frequency on this one is 220 Hertz, the frequency for the first harmonic would actually be half that, because there's half the amount of loops. So that would be 110 Hertz. So to consolidate, we've got a fundamental frequency of 110 Hertz. We've also got a mass per unit length of 2.258 times 10 to the minus 4 kilograms per meter. And we've got a tension of 4.905 newtons. So now we're in a position where we can find the length, L. So the equation, frequency is 1 over 2L, multiplied by the square root of T over mu. Then just rearrange to find L. So L will be equal to 1 over 2F T over mu. Then it's just a matter of putting our numbers in. So the length is equal to 1 over 2f. So 1 divided by 2 times 110 is 1 divided by 220. Square root of the tension, 4.905, divided by mass per unit length, 2.258 times 10 to the minus 4. So that will give a length that is equal to 0.67 meters. Hopefully that's okay, and your confidence with standard waves should have increased by now. If you made any mistakes and you want to attempt the question again, just rewind, and have another go. But I hope that's helped. Thanks for watching, and I'll speak to you soon.